The day school killed your genius, what Richard Feynman saw that nobody wanted to hear you, were born a scientist. Not metaphorically, not poetically. Literally, the moment you were old enough to grab something and drop it just to watch it fall, you were running experiments. The moment you asked why for the 47th time in a single afternoon, you were doing philosophy. The moment you took apart your toy just to see what was inside, you were doing engineering. You came into this world wired for discovery. And then something happened. Something slow, something systematic, something so normalized that almost nobody questions it. Something that took that burning, restless, unstoppable curiosity and quietly, efficiently, methodically, turned it off. We call it education. Now, before you dismiss that as the kind of thing rebellious teenagers say on their bedroom walls, stay with me. Because the person making this argument wasn't a dropout or a counterculture radical. He was one of the greatest physicists who ever lived, a Nobel Prize winner, a man who helped build the atomic bomb, decoded the mystery of superfluidity, and revolutionized how scientists think about quantum electrodynamics. A man who, when he sat down to explain something, could make a room full of physicists feel like they were hearing it for the first time. His name was Richard Feynman, and what he saw in classrooms across America and eventually across the world troubled him deeply. Not because students were failing, but because students were succeeding at entirely the wrong thing. Let's go back to a moment in the early 1950s. Feynman had just returned from Brazil, where he'd spent nearly a year as a visiting professor. Brazil was vibrant, beautiful, energetic. The students he encountered were enthusiastic. They worked hard. They showed up, and when the time came to recite formulas, definitions, and textbook explanations, they were flawless. Feynman was initially impressed. Then he started asking questions. Not the kind of questions that appear at the end of a textbook chapter. Real questions. The kind that require you to actually understand what the words mean, rather than just what order they appear in. He asked students about polarized light. They knew the definition perfectly. They could recite it word for word. But when he held up a piece of polarized glass and asked them to figure out what angle it was cut at by using what they knew about reflection from the surface, a practical application of the very principle they'd just recited, they stared at him blankly. They knew the name of the thing. They had no idea what the thing actually was. Feynman described it this way. The students had learned the words, but not the music. They could hum the melody perfectly if you gave them the sheet, but they had never actually heard the song. Stop. Think about that for a moment. These weren't lazy students. These weren't bad students. These were dedicated young people who had worked hard, memorized diligently, and performed well by every conventional metric. And they understood almost nothing. Not because they were incapable of understanding, but because understanding had never really been the goal. The goal had been recitation. And recitation, Feynman realized, is the enemy of understanding. Now, you might be thinking, okay, that's a cultural issue specific to Brazil in the 1950s. Surely modern education is different. Surely decades of reform have solved this. Here's where it gets interesting. Walk into almost any high school physics classroom today. Watch what happens in the days before an exam. Students are drilling formulas. F equals ma, E equals mc squared, PV equals nRT. They're writing them on index cards, repeating them under their breath, building elaborate mnemonic devices to ensure they don't forget the arrangement of letters and numbers long enough to transfer them onto a test paper. Ask those same students a week after the exam to explain what any of those formulas actually means in terms of the real world they live in. Ask them why a heavier object and a lighter object drop from the same height, hit the ground at the same time. Ask them why the sky is blue and the sunset is red and they're the same sky. Ask them why you can hear a car coming around a corner before you can see it. Silence. Or worse, a recitation of a definition that contains the answer in some technical sense, but explains nothing at all. This is not a coincidence. This is a design feature, not a malicious one, not a conspiracy. Just the natural outcome of a system that needs to measure things, and finds it much, much easier to measure whether a student can reproduce a formula than whether a student genuinely understands the universe that formula describes. Feynman had a name for the most dangerous version of this failure. He called it cargo cult science. The story behind the name is extraordinary. During World War II, Allied forces set up military bases on remote islands in the Pacific, islands whose inhabitants had never encountered industrialized civilization. These islanders watched in fascination as enormous metal birds landed on cleared strips of land, disgorging unimaginable quantities of food, tools, medicine, and goods. After the war ended, the planes stopped coming. But the memory of the abundance never faded, so the islanders did something entirely logical given what they knew. They built wooden replicas of the airplanes. They cleared new runways. They constructed huts that looked like control towers and sat inside wearing headphones carved from wood, speaking into bamboo microphones, mimicking every ritual they had witnessed the soldiers performing. They had all the form. They had none of the substance. And of course, no planes came. Feynman looked at how science was being taught and how it was being practiced in certain fields and saw the same pattern. The rituals of science, the technical language, the formal structure, the graphs and citations and references, the appearance of rigor, all present. But the actual engine of science, the genuine wrestling with whether your theory actually explains the thing it claims to explain, whether you might be fooling yourself, whether the data truly supports the conclusion, missing. Replaced by the wooden headphones, replaced by the bamboo microphone. And he wasn't just pointing at students, he was pointing at researchers, at institutions, at entire fields of inquiry that had learned to speak the language of science without practicing the actual discipline of it. The cargo cult metaphor is so precise it's almost painful, because it's not that these practitioners were dishonest. They genuinely believed they were doing science, just as the islanders genuinely believed they were doing the thing that would bring the planes back. The tragedy is not cynicism. The tragedy is sincere, dedicated, hard-working people who learned the costume and never met the creature wearing it. Now here is where Feynman's critique becomes personal, because he didn't just observe this problem, he diagnosed its cause. And the diagnosis points directly at how we are taught to think from our earliest years in school. Imagine you're 5 years old. You're walking outside with a family member, a father, an uncle, a grandfather. It doesn't matter. And you point at a bird and ask what it's called. The adult says, "That's a chestnut-backed chickadee." You nod. You feel like you've learned something. But here's what Feynman actually said about this exact kind of moment, drawing from his own childhood with his father. His father would do something different. His father would say, "I can tell you that bird's name in 15 different languages. In English, it's called a chestnut-backed chickadee. In Portuguese, it's called something else. In Chinese, something else again. And when you know all those names, you will know absolutely nothing about the bird. But notice how the bird's feathers work. Notice how it moves. Watch what it does when it lands. Watch how it pecks. Now you're starting to know something about the bird. The name tells you how other humans have labeled the thing. It tells you nothing about the thing itself." This is first principles thinking, and it is the precise opposite of what most education trains students to do. First principles thinking means you strip away the labels, the inherited assumptions, the conventional wisdom, the textbook definitions, and you go back to what you can actually observe, verify, and reason from directly. You ask not, "What have I been told this is?" but "What is this when I actually look at it?" Feynman was a master of this. When he encountered a problem, he didn't reach for the established framework first. He asked, "If I didn't know any of the standard approaches, how would I even begin to think about this? What do I actually know for certain that I can build from?" This is not easy. It's actually much harder than memorization. Memorization you can do while your mind is somewhere else. First principles thinking requires complete, uncomfortable, sustained attention. It requires you to sit with not knowing long enough to actually arrive at understanding, rather than just a convincing sounding placeholder for understanding. And traditional education, by its structure, punishes this approach. It punishes it economically. The student who thinks from first principles takes longer. They ask uncomfortable questions. They sometimes arrive at different answers in the textbook, and they want to discuss why. They don't fit into the scheduled 50-minute block. They are difficult. They are inefficient. They get lower test scores while understanding more deeply. So the system quietly selects against them, or more precisely, quietly selects against that behavior, even in students who are capable of it. It trains the first principles instinct out of children who arrived with it in abundance. But here's where it gets interesting. Because Feynman's critique isn't ultimately a counsel of despair. He didn't believe that curiosity, once suppressed, was gone forever. He believed, and demonstrated throughout his entire career, that it could be recovered. That the original, native scientific instinct that children bring into the world could be reawakened, even in adults, even in people who had been thoroughly processed by conventional schooling. The method he advocated is so simple it sounds almost trivial, but its simplicity is deceptive. He called it, explain it simply, or admit you don't understand it. The full version goes like this. When you want to test whether you truly understand something, try to explain it clearly enough that a bright 12-year-old with no background in the field could follow your reasoning. Not the definition, not the technical framework, the actual underlying reality the definition is trying to describe. If you can do that, if you can construct an explanation that a smart young person could follow without specialized vocabulary, you understand it. If you can't, you have memorized it, and it's a completely different thing, and you should go back to the material and keep working. This test is brutal. It is absolutely merciless. You can be a fully credentialed expert in a field. You can have published 20 papers, and if you sit down and actually try to explain the core principle of your own research to a curious teenager in plain language, you will very quickly discover where your genuine understanding ends and where you have been coasting on technical language that makes insufficient understanding invisible. Try it right now. Pick something you believe you understand: gravity, evolution, supply and demand, the immune system, whatever you feel most confident about. Now explain it out loud, in plain English, with no jargon, from first principles in a way that someone who has never studied the subject could actually follow and verify for themselves. Go ahead. I'll wait. Most people doing this exercise honestly for the first time are stunned, not because they are ignorant, they may be genuinely knowledgeable, but because the gap between "I can use this correctly in context" and "I can explain what this actually is" turns out to be enormous. And traditional education almost never asks you to cross that gap. Now let's follow this further, because there's a deeper dimension to Feynman's critique that touches on something almost philosophical about the nature of knowledge itself. Feynman was obsessed with the difference between knowing the name of something and knowing something, and he extended this into a broader meditation on the difference between education that transfers labels and education that develops genuine capacity. The distinction matters enormously for what students are actually capable of doing after they leave school. A student trained primarily in label transfer can recognize situations they have seen before and apply the correct formula. They are, in essence, a sophisticated pattern matching system. Put them in a familiar context, and they perform beautifully. Change the context, alter the framing, present the same underlying problem in a different costume, and they are lost. A student, trained in genuine understanding, can encounter a completely novel situation and reason about it from what they actually know. Because what they know is not a collection of labels applied to things. It's a genuine grasp of how things actually work, which transfers across contexts because the underlying reality doesn't change when the framing does. This is not an academic distinction. This is the difference between a scientist and a technician, between a thinker and a retrieval system, between a person who can navigate genuinely new problems and a person who can only navigate problems that resemble problems they've encountered before. Feynman believed, and his career was a living demonstration, that the goal of education should be to produce the first type of person. Not because technicians are useless, they're not, but because the problems that actually matter, the problems that advance human knowledge and improve human life, are almost by definition novel. They're problems we haven't encountered in this exact form before, and no amount of pattern matching against previous examples will solve them. The Wright brothers were not aeronautical engineers in any credentialed sense. They were bicycle mechanics who thought from first principles about what a flying machine would actually need to do and why. Watson and Crick were working in a field where many of the most credentialed experts were confidently wrong about the structure of DNA. Feynman himself, when he was investigating the Space Shuttle Challenger disaster as part of the Rogers Commission, famously ignored the official bureaucratic process, walked into a cafeteria, dipped a piece of O-ring rubber into a glass of ice water, and demonstrated in about 30 seconds, with no specialized equipment, what the entire official investigation had been dancing around for months. First principles thinking. A rubber ring. A glass of ice water. the willingness to actually look at the thing rather than at the category you've placed the thing in. There's a thought experiment worth sitting with here. Imagine two students, both intelligent, both hardworking, both genuinely interested in physics. Student A has been trained in the traditional method. She's memorized every formula, assayed every temple, assayed every test, and graduated near the top of her class. Ask her anything on the curriculum and she gives you a letter-perfect answer. She is, by every official measure, an excellent student. Student B has been trained in Feynman's method. He has spent half as much time on formulas and twice as much time asking, but why? He has argued with textbooks. He has drawn pictures of what equations mean in real space. He has failed multiple tests because he spent time trying to derive things from scratch rather than just memorizing the standard derivation. He is, by official metrics, a mediocre student. Now put both of them in front of a problem that neither has seen before. A real problem. Something at the frontier. Something where there is no established procedure to apply. Which student do you want working on it? Feynman knew the answer. He had seen both types. He had taught both types. And he believed, with a kind of conviction that comes from direct observation rather than ideological preference, that the single most valuable thing education could do was develop the second kind of student. Not at the expense of knowledge. He was fanatical about actually knowing things, but in service of genuine understanding, which is the only knowledge that compounds. Here is what makes this more than a critique. Here is the part that should feel genuinely exciting rather than just sad. The capacity Feynman is describing, the first principles thinking, the genuine curiosity, the willingness to say, I don't actually understand this yet, rather than hiding behind technical language. This is not rare. This is not genius level. This is the default operating mode of every child ever born. Watch a 3-year-old with a magnifying glass. Watch a 6-year-old disassembling something. Watch an 8-year-old who has just discovered that asking "but why" is a question that has no final answer, that every answer can be questioned again, and who is delighted by this rather than frightened. That is not a genius. That is a human being doing what human beings naturally do. What we are built for. The question is not how to create this in people. It already exists. The question is how to stop destroying it. Or, for those of us who have already been through the system and feel the curiosity diminished, how to find our way back to it. Feynman's answer was, start asking real questions again. Not exam questions. Not questions you already know the answer to. Questions where you genuinely don't know, and you're willing to sit with the discomfort of not knowing long enough to actually find out. Pick something you use every day and actually understand nothing about. Your phone, your car engine. The fact that you can read these words at all, that patterns of light on a screen can carry meaning across from one mind to another. Ask why. Not once. Keep going. Follow the chain of why until you hit something you actually don't know, and then instead of accepting a label as a stopping point, go find out. You will discover, somewhere in that process, that the curiosity you thought was gone was just buried. It's still there. It was always there. The system managed to make it inconvenient for a while, but it is remarkably resilient. Feynman once said that he thought he had been very lucky to have been taught, from early childhood, that the difference between knowing the name of something and knowing something was the most important distinction there is. Most of us were not that lucky, but luck isn't destiny. And knowing the distinction now is worth something. Worth quite a lot, actually, because the moment you can tell the difference between a label and an understanding, between a formula and the reality it describes, between the wooden headphones and the actual technology, you can no longer be fully fooled by the cargo cult. Not in science, not in education, not in any field where impressive-sounding language is used to obscure the absence of genuine comprehension. That kind of intellectual immunity is, in some ways, the most valuable thing education could give you. More valuable than any specific piece of content, more durable than any credential. And the beautiful, slightly subversive truth that Feynman demonstrated with his entire career is that this immunity doesn't require a special institution or a special teacher. It requires only one thing: the willingness to actually want to understand. Not to seem like you understand, not to have a label to point at, but to actually, genuinely, uncomfortably, persistently want to know what the thing actually is. That impulse, that refusal to accept the name of the bird in place of the bird itself, is the whole engine. Everything else follows from it. You were born with it. It was the first thing you ever did. It's still in there. Go find it.